Good afternoon to all the students. Today, in this session of fuels and combustions, we are going to see the thermodynamics of combustion. In the last session, we have seen what are the different types of fuels which are used. That can be our petroleum or alternative fuels. We have seen the properties of fuels, that can be gaseous fuels or the liquid fuels. We have seen the types of flame. We have seen the flameless combustion. Okay. Now in today's session, we are going to see what are the important factors, that is the thermodynamics of the combustion process. Now here, before we start this session, this thermodynamics of combustion is divided into introduction. What is the motivation behind learning this thermodynamics of combustion? Then thermodynamic properties, laws of thermodynamics, stoichiometry, thermochemistry, adiabatic flame temperature, and chemical equilibrium. So first of all, we should know the understanding of thermodynamics. The thermodynamics is a combination of two words. First is thermo and next is dynamics. Okay, so these are, the thermo is related with the heat. It is a Greek word of heat, and dynamics means the study of dynamics of heat. And this thermodynamics deals with the energy. Okay, energy and its conversion from one form to another form. Therefore, in order to properly understand the thermodynamics, we have to understand what is meant by system, surrounding, and universe. Here in this picture, you can see, so this is the system. Okay, the system is that region on which we are focusing our attention in order to understand it. Okay, so the system, this is the system, and whatever which is around the system is called as a surrounding, and the system and surrounding are separated by this boundary. Okay, so this boundary is necessary to distinguish between system and surrounding. The system, surrounding, okay, both of these comprises the universe. Okay, now here the system, here this system we can categorize into three types. One is the closed system, one is the open system, and third one is the isolated system. And the categorization of this system is based on the mass interaction. Okay, when the mass of the system remains in the system, we call it as a closed system. Open system means when there is an interaction of the mass, okay, from the system, okay, to the surrounding, we call it as an open system. And third, we call it as an isolated system. In isolated system, there is no interaction of mass as well as energy from the system. Okay. Now, the next important part is the thermodynamic properties. The thermodynamic properties are divided into two basic forms. One is the intensive property and other one is the extensive property. Okay, the intensive property comprises the properties of the system such as pressure, temperature, specific entropy, whereas the extensive properties comprises mass, volume, enthalpy, and entropy. Now, the basic categorization of intensive and extensive properties, okay, we see here the intensive property is independent of mass, okay, and this extensive property is dependent of mass. Okay, now this is the basic two forms. Now here there is one question: is ideal gas law valid for the combustion problems? There is the ideal gas law. What is that ideal gas law? PV is equal to nRT. Okay, so this one is the basic ideal gas laws. And these gas laws can be applicable to the combustion, including high temperatures and resulting into low density. Okay, now here this P represents the pressure, this V represents the volume, this N is total number of moles of the gas, R is the universal gas constant, and T is the temperature. Okay, so this formula is used, okay, for this, and in this formula we can see this PV, these are nothing but it are the properties of the we can say the gas which we are dealing in our system. Okay, now the next important property is the compressibility chart for air. Now see here, as we increase or decrease the pressure of the air, the volume of the air changes. Okay, and the change in the volume with change in the pressure is related with the factor which we call as a compressibility. Now for ideal gas, the compressibility which we call by letter Z is equal to 1. Okay, means the PV is equal to mRT relation is valid for the gas whose compressibility is equal to 1. But in the practical applications, any gas such as air, okay, if we heat it, okay, and at that time if we increase the pressure and see the change in the volume, this relationship no longer remains linear. Okay, now therefore in this case the use of ideal gas equation PV is equal to mRT will not give you the accurate result. Okay, but if you modify this formula based upon this compressibility, you are able to get somehow accurate results. Therefore, the compressibility factor also plays a very important role whenever we are dealing with the thermodynamics of combustion. Now, next important point is we have to study the mixture of gases. When we are using a mixture of gases, then how we have to do the calculation? Now here, the first important parameter is the number of moles. Okay, the total number of moles. So see here, this one is a container, and here the container consists of the mixture of gas, and the total number of moles, okay, of a particular gas we should be knowing in it. Suppose this Na represents the number of moles of constituent A gas, Nb represents number of moles of constituent B gas, Nc represents number of moles of constituent C gas. Okay, now see, so there are different gas, so we can see here up to Ni. Okay, Ni represents N high number of gases. Now, if you want to determine the total number of moles in this container, so this is the formula. N total is equal to Na plus Nb plus Nc plus up to Ni. Okay. Now, here, if we divide this formula by N total, so we get here N total divided by N total is equal to 1 is equal to Na upon N total is Xa plus Nb upon N total is Xb plus NC upon N total is XC, so up to XI. Okay. Now here, what is this XA, XB? These are the mole fractions of species A or B. Okay. So total number of mole becomes very difficult to calculate, but to determine this mole fraction of species is quite simpler. Therefore, we have modified this formula. Now the total mass of the mixture is given by M total. Okay. Now here M total is nothing but mass of constituent A plus mass of constituent B plus mass of constituent T up to Mi. And if we divide this equation by M total, we get 1 is equal to Ya plus Yb plus Yc, where Ya and Yb represent the mass fractions of species in that gas. Okay. Now here, the next important formula is this summation of total Y is nothing but the total mass index is given by Mi divided by M of mixture. Okay. Now here, this formula is further given as Ni into Mw, M into Wi divided by N into Mw of mixture. Okay. Therefore, this M into W of mixture is given by summation of total Xi M into Wi. Okay. Now here also this formula we can modify, okay, by using these equations. Here this is that equation. So here the N total we get from PV divided by RT is nothing but the N total. To determine this N total, we must know the value of P, value of V, value of R, and value of T. Okay. Suppose we are substituting this N total value, okay, in equation number 1. So here we put N total in here. Similarly, Na value here, Nb, Nc, Nt. So this Pa represents this partial pressure. Okay, and this formula here, it corresponds to the partial pressure of the species. And if you do the additions of these partial pressures of all the constituent gases, that is equal to the total pressure of the gas. And this law corresponds to Dalton's law of partial pressure. Okay. So what does this Dalton's law corresponds? So this one is a container consists of this number of mixture of these gas constituents. And if you want to know the total pressure of it, or if you know the total pressure of these gas molecules, that is nothing but it is the summation of the individual gas constituents in this container. So here the statement of the Dalton's law is the total pressure of a gaseous mixture is sum of the total pressure which each component will exert if it is alone occupies the same volume and temperature of the mixture. Okay. Now the analogy of this Dalton's law is given by the Gibbs law. Now this Dalton's law corresponds to this partial pressure or the total pressure, but this Gibbs law, it corresponds to the internal energy. So what does this Gibbs law corresponds? The internal energy of a mixture of ideal gas is equal to the mass fraction weighted sum of the internal energy of individual components of the mixture. So this there is a systematic analogy between the Dalton's law and the Gibbs law, whereas the Dalton's law relates with the pressure and the Gibbs law relates with the internal energy. The internal energy is denoted by a small letter U. Okay. Now, the next important term is the enthalpy and internal energy. Before that, I will tell you what is meant by the specific terms. Now, you suppose there is internal energy. the internal energy can be divided between total internal energy and the specific internal energy. The specific internal energy is nothing but the energy per kg, okay, of the mixture. Okay, when we are dealing with the 1 mole, okay, or per kilomole, okay, of mass or the mole fraction, then we use the specific word. Okay, so here the internal energy per kg is denoted by a small capital letter U, is nothing but summation of the mole fraction into the internal energy of that molecule. Okay, so if there are n molecules, so we have to do the addition of the internal energy of all the molecules, okay, and then we get the total internal energy of the mixture. Then next is the mass specific internal energy of the mixture. Okay, now this one is the mass specific. So what is the difference between mass specific and specific? The specific internal energy deals with the kilomoles and the mass specific internal energy deals with per unit kg. Okay, now next important part is the specific enthalpy. Here the specific enthalpy is similar to the summation of the enthalpies of the individual gas constituents in the mixture per kilomole, okay, and the mass specific enthalpy is the summation of all the constituent gas molecules, okay, per kg. Okay, now the enthalpy of the species, okay, this one is a very important term. So if there is a mixture, the mixture formula we have seen here, but what about the enthalpy of individual species in that gas container? So for that we are having the formula such as it is a summation of the heat of formation. This heat of formation is due to the bond energy. Whenever any compound is formed, okay, or any molecule is formed, there is an interaction of the heat energy. So that heat energy we have to consider when we are dealing with the enthalpy of the specific gas element plus the sensible enthalpy, and this sensible enthalpy is associated with the temperature. So as the temperature of the gas molecule increases, the correspondingly the enthalpy of the gas species also increase. So by having the addition of this enthalpy of formation and the sensible enthalpy, we can get the total enthalpy of a species. Now the next important term is the internal energy of a species. Now the internal energy of the species can be obtained as the internal energy, okay, when it is formed plus the sensible internal energy, okay, and this is associated with the temperature. Now see here, in this case, whenever we are dealing with the enthalpy, we are taking here the Cp value. And whenever we are dealing with the internal energy, we are getting here Cv value. Because this enthalpy term is related with the open systems, whereas the internal energy term is related with the closed systems. Now here, there are the different species of the gas. And these are the standard species such as oxygen, hydrogen, water, carbon monoxide, carbon dioxide, methane, propane, butane, kerosene, nitrogen dioxide, and nitric acid. Here we are having the chemical formula for this gas species and the state, whether it is in a gas or a liquid. And in this last column, we are described what is the heat of formation at 25 degrees centigrade and 1 atmospheric pressure. Suppose for the oxygen and hydrogen, we are having the heat of formation at 0. That means whenever this element is formed at 25 degrees centigrade and 1 atmospheric pressure, during the bond interaction, no energy is entered into the system or leaved out of the system. Now, in case of the water, the value is minus 242 kilojoule per mole. That represent the minus sign indicates the heat is added to the system, and therefore the heat is required for the formation of the water bond, and therefore in this the heat is supplied to system. That is why this is negative. Now, in case of this nitrogen dioxide, the value is 33.9, and this value is a positive value. That indicates the heat is liberated from the system to the surrounding during this process. Okay, so specifically, this is the exothermic process, liberation of heat. Now, the specific heats, the next important property we call as the specific heats. Now, the specific heat can be of the constant pressure and the constant volume. And the specific heats are the function of temperature. Okay, here this is a graph. Okay, now in this graph, you can see the internal energy of is a function of transitional energy, vibrational energy, and the rotational energy. And the variation of the specific heat with temperature is caused due to this vibrational energy and the rotational energy. Okay, now now but there are certain monoatomic gases, and in case of these monoatomic gases, it is found that the specific heats of monoatomic gases do not vary with the temperature. And the reason for this is because in this case, the specific heat of these monoatomic gases is by the transitional energy, and it is not by the vibrational or the rotational energy. And due to this specific heat remains constant and do not vary with the temperatures. Okay. Now here, this one is the thermochemical data. Okay, this one is for the water H2O. So what is the value of specific heat at the different temperatures? Okay, now in this case of water, we can see the value of specific heat changes as the temperature changes. Enthalpy changes as the temperature changes. Okay, now this delta HF, it represents the enthalpy of the we can say vaporization. Okay, now this one is the properties which we are necessary for determining the enthalpy. Suppose we want to determine the enthalpy at a particular temperature. It is nothing but the addition of this delta HF plus HI at a particular temperature minus HFI at 298 degrees centigrade. And this is for the enthalpy of the formation, and this represents the sensible enthalpy. Okay, with help of this formula, we can determine what is the enthalpy. Now the question for you or your homework is, what is enthalpy? What is significance of enthalpy during the combustion process, that you have to study. Okay, so today I am going to stop this session. Okay, I will conduct the next session in the tomorrow I will conduct your next session. Okay, the recorded lecture is posted on this YouTube. You should go through the lecture before coming to the next session. So thank you.